Good morning, everyone. Thank you for your time today. Today's topic, as Cheryl mentioned, antenna distribution. A lot of times we kind of look at topics that we think are pertinent to folks. We try to also groom through questions of our support team. What gets asked a lot, what's misunderstood. And so one of the things that popped up was antenna distribution, which is hopefully you'll find today a lot of the best practices that Kristof and Jason, who will be presenting most of this material on. And we'll get into a quick bio of who we will be hearing from today. Kristof Jeuris is 20-year plus veteran of the live production industry. Kristof has also spent extensive amount of time in the cable TV RF research and development area. And where this is unique is that it's provided him with deep-seated knowledge in digital RF modulation schemes. And Kristof hails from Belgium as one of our application engineers. Our second presenter today will be Jason Waufle. Jason is a professional audio specialist who excels in RF coordination, distributed antenna systems, and also system design. Prior to joining the Shure team, some of Jason's RF experience includes the likes of the Super Bowl as well as the Grammys. As market development specialist within the pro audio vertical, Jason covers the southeastern United States. I am market development on the systems side in the southeastern United States. So today, some of the topics that we'll be looking at, hopefully we'll get to that. There we go. Oh, there we go. Today's agenda, introduction to antenna distribution, again, benefits and why to use it, understanding the importance of this. A lot of times these are things that folks feel can be value engineered out. And some of this information is just good information to understand why you do need this, and also just demystifying antenna distribution. It's really not as difficult as what a lot of people think, and then actually showing you some of these examples of how quick and simple antenna distribution can be once you know the basics. And then, of course, we'll finish up with some question and answer session. And with that, I would like to kick it over to Kristof.
Thank you so much, Michael. Just before we move on, I have a but first. Unfortunately, we're a bit limited for time on this webinar today. So just in the interest of time here today, we're not really going to dive deeply into wireless fundamentals. We're not going to explain what the different antenna types are, what diversity reception is, and what are multipath effects and cable types, for example. But we do like to educate you on all of these topics as well. So if you're really keen to learn, feel free to go to our website, shure.com, to our support page, and there you can find a link to the Shure Audio Institute. And there's plenty of trainings on all those topics on there as well. So what will we cover today? We're going to look at antenna distribution, what the differences are in distribution and combining, and we're really going to focus on UHF single carrier microphone systems. So just to bring that up now already, that we will not be talking about DECT-based systems like our MXW system and 2.4 gigahertz based systems like MXEW. So with that, Jason, what can you tell us about antenna distribution? Why would we need it in the first place?
Yeah, thanks, Kristof. I seem to be having a bit of a camera issue. Hopefully you can hear me okay.
Yep, we can just fine.
Trying to figure out if I can get one back. But yeah, antenna. Why do we use antenna distribution? Kind of the kickoff to this webinar, I suppose. And there's a number of exceptional reasons. The first reason is that you get to use one set of antennas for multiple receivers. So if you're in a situation where you have multiple RF receivers and you need to simplify your setup, RF distribution is the solution for you. And why is that important? Obviously, we're going to dive through that, but essentially it's preventing interference between closely spaced receivers and giving you best practices in terms of your antenna placement and some of the more advanced functions of RF like filtering and tuning happens through antenna distribution as well. We remove extra failure points. If you only have one set of antennas and one DA, you don't have multiple cables run for every receiver and multiple antennas run for every receiver, so you have less points of failure. And this allows you additionally to expand your system for more zones and more coverage when getting into larger distribution setups. I mentioned briefly about proper antenna placement. We're going to touch on this not a ton, but it is a part of this conversation based on that distribution allows you to really use one set of antennas per zone and get those placed properly. So we're avoiding walls, we're avoiding parallel surfaces. We're not going to dive into the deep conversation that is antenna placement and antenna types today. But antenna distribution is the process that allows you to really get your antennas placed properly. Some examples that we want to point out of what is not good placements of antenna. This is an A and a B inside of a rack. If you know much about RF, you know that this is now stuck inside of a metal cage. Metal prevents RF, and so you'd want to distribute those antennas in a way that was achieving better results for that antenna placement. Those are also likely off axis from the polarization of your wave. They are on a horizontal plane, not the vertical plane. So getting those outside of the rack using antenna distribution or cabling to do so. This is also not a great example of proper antenna distribution. You'll notice the spacing between those antennas is not the minimum required spacing for proper reception. This conversation is a little bit longer for this page specifically in terms of wavelength, doing the math on how long your radio wave is, how much space it needs to go through a cycle, at least a quarter of a cycle, and the distance between those antennas is not proper. So we're going to dive into what are some of the proper ways to do antenna distribution. And Kristof, I think there's some specific questions that you've gotten about how to demystify some of the basics of antenna distribution.
Yep, there are indeed. I can say we get loads of questions about RF on a daily basis, and there are too much questions to handle in such a short time. But we just want to take you through some of the ones that pop up most and things we get asked on a very regular basis. So one of the questions we get asked very often is just how many systems can we put on one antenna? I mean, I had 4 systems before. I just purchased 2 extra channels. Do I need any extra antennas to support all those extra new systems? And we can very fundamentally say, no, there is not a limit on how many signals you can receive on a single antenna. The only thing you really have to look at is that your antennas that you're using is within the same frequency range of the receiver unit you are using. So make sure that those antennas are spec'd in the same frequency band as the receiver that you've got there. And in the case of transmitting systems, there are power limits to antennas. However, it's very unlikely in our industry that we easily hit those power limits on transmission. If we look at receiving systems, the chance of hitting those power limits is slim to none. So there definitely there isn't really a limitation. So theoretically, no limit to how many channels you can put on an antenna. Then even take that a bit further and say we have a rule of thumb, and that is that for every setup, no matter whether it's 4 channels or 400 channels, you always have 3 antennas per zone. And with 3 antennas, we mean 2 antennas for diversity reception for your receivers, and then we put 1 antenna for transmission. Obviously, there's proper antenna spacing requirements where we have to make sure that you keep appropriate separation between those 2 antennas, not to interfere with each other. And then the one exception I've put in here is well, excluding multi-zone applications, because the rule of thumb for 3 antennas per setup is true as long as you're receiving and transmitting those signals in one specific area. So we've got a bit of a use case example here. This whole setup, which was just over 100 channels, in the end was all connected to 2 antennas. So no matter what setup you have, whether it's 2 receivers, 4, 8 or more, the rule of thumb there is receive them on 2 antennas. So another question we get as well is, more gain is better, right? People always think, I've got an amplifier on my antenna here, and well, it says plus 12, and plus 12 is more signal, so yay, more signal, I'm happy. Well, unfortunately, that isn't the case. Much like you dial in the gain on a microphone input to a mixing desk, we have to dial in the gain to an RF input on a receiver. And that's exactly the reason why there is a gain switch on our active antennas. And basically the reason that amplifier is there is not to boost your reception, it is there to compensate for cable losses. And that's the only reason it's there. That also explains the -6 dB pad switch on there, because in this example, we're using an LDPA antenna, which has 6 dB of gain just by the antenna design. If you have a really short cable, you can take that 6 dB back off to land at 0 at your receiver. So to summarize, more gain is not better. We'll come back to that a bit later in the slide. I can explain you how to set that gain properly. So another question we get often is, I've got an analog microphone system. I'm switching to digital now. I'm changing from UHFR, for example, to QLXD or Axiom Digital or any of our other systems. Can I use my antennas? Can I use my distros? Do I need new equipment? And the simple answer there is, an antenna does not care about modulation type. A distribution unit does not care about modulation type. So if you have existing equipment and it works well, and it is in the same frequency band as the new system you purchased, you can more than happily mix and match those systems together on that distribution unit. Obviously, when you're looking at cascading, when you're looking at combining pieces of equipment, make sure that you're all in the same frequency band. That's the big if there. But that applies even if you're combining analog systems or you're combining digital systems. So that's some of the stuff I heard. I don't know, Jason, what are some of the things people have asked you?
Yeah, those are really good questions. A couple common ones that come my way are, what's the difference between a transmit and a receive antenna? When can they do both? And where can you use those? And so typically, an antenna is bidirectional. The physics of an antenna design makeup says that it can transmit and both receive, regardless of which type it is. What really changes that is when you put an amplifier onto those antennas. So as you were showing a couple slides ago, talking about more gain not being better always, is if you have an amplifier on your antenna, it is likely a receive only. There is a comment in there unless you have the plexer, which we don't see a ton in our industry. But rule of thumb here is that antennas work both directions and active antennas are receive only. It is worth noting here that the combiner and or distro, which we'll talk about the differences here on the next slide, is unidirectional. So that's kind of the next question is, what is the difference between combining and distribution? There's an antenna distribution system and a combiner, and the difference is, it's kind of in the name. So a combiner is taking multiple sources and we're combining that into one. So we traditionally in a IEM system or a IFB system, where you have multiple transmitters, combining them into one singular transmit antenna. And then there's distribution. You're taking a pair of antennas and you're distributing the receive signal from that side to receivers. There are some kind of more advanced applications where the receive and transmit line that I just drew out in terms of combining and distributing are not accurate, but for the rule of thumbs, combining is for your IEM and transmit side, and distribution is for your IEM and receive side. Speaking of transmission, I think one thing we talk about or often looked over are the power ratings of your equipment. All units have maximum power ratings, and this often comes in play with cost and tiered level. So it's not much of an issue on the receive side because the receive side is often very low power, you see there. However, the transmit side is where the significant power comes into play. And you want to make sure that you check your manual of the products that you have in line to make sure that you are not exceeding the power rating for that product. Some examples here, there's the PA421, 250 milliwatt input. The UA221, the splitters got 1,000 milliwatts total. So just keep in mind as you're on the transmit side of things and setting up your distribution, you should check your manual for the power in the products to make sure you're not exceeding that. Generally speaking, products come in kind of families and tiers that make sense for one another, and those products are designed to work well with one another. But in a scenario where you're matching, make sure you check your power settings. And then lastly, should I always use the same antennas in a pair? This is to say, do I need a dipole on both my A and my B receive sides? Or can I use, in this photo, an LPDA on the A and a dipole or omnidirectional on the B side? Yes, you can do. There is no law that says you have to be matching antennas on both sides. What the reality of this situation comes down to is that you should be trying to match the system gain through all of the elements in your A signal chain and your B signal chain of receive. You're trying to get those to be even or as close to even as possible. And ultimately, hopefully, at what we call unit gain from a RF standpoint. So yes, you can use a PDA on one side and on the other. You should be doing the math to figure out how to make sure they're balanced. That we're going to kick into that a little bit here. As Kristof, I think you're going to talk to us about how to set up a small system and dive a little bit deeper into what I just spoke about.
Yeah, exactly. Thank you, Jason. So we've already talked about more gain is not better. We've talked about it's important that you match your antennas and that you've got similar power levels at your A input and your B input. So I just wanted to show you this chart that explains a bit how you go about doing that calculation. So what we've got here is basically an antenna which can be gained from -6 to +12 dBs. Behind it, we've got a 7 dB cable loss. So what I'm going to do at that point is basically select a +6 setting on my antenna. So I end up at a -1 dB loss at the entry of my line amplifier. On that amplifier, I've got a choice of +6 to +12. Basically, because I come in at -1 and I'm gonna lose another 4 dBs in the cable between this amplifier and my receiver, I'm gonna select the +6 setting, which is gonna give me a +1 dB signal level at the entry of the receiver. So that's kind of the calculation you'll have to do for whatever RF distribution system you'll make, and it's very important that you do that calculation for the A side and the B side if they are not similar, and make sure that the power levels on both A and B side are the same. So we advise, if you do that calculation, you're never going to be able to hit absolutely zero, or in very rare occasions. But whatever you can do to try and keep that level at ±5 dBs, you're typically in a safe zone to get a good signal reception. So imagine we've got not a single receiver, but you want to go to multiple receivers. Then the easiest way, by far the easiest way to split that signal across two receivers is by using a passive splitter or a passive combiner. Again, as we've spoken about, as long as there's not an amplifier on it, most RF components are bidirectional. So this passive splitter will give you about a 3.5 dB loss. It can handle just up to a watt of power. And the easiest way to use this is if you've got two receivers, put it in between there, one on the A, one on the B, and you can receive on two receivers the same antenna at the same time. Unfortunately, we see this type of T-splitters or BNC splitters in the field sometimes used as an antenna splitter. Please do not use these. You're going to run into a whole lot of impedance mismatch issues, and they do not work properly for RF distribution. Even worse, if you use them on transmitters, on in-ear transmitters, there's a good chance that you may damage the RF output of your in-ear transmitters. So please do not use these in RF distribution. So Jason, I've just explained what passive splitters are. Can you just talk us through a couple of examples of what we could do with these passive splitters?
Yeah, absolutely. Passive splitters are kind of the gateway to antenna distribution and the beginning of how you start to distribute some antennas for some simple single level DA systems. So here we see a pair of single rack or half rack QLXDs. Without these passive splitters, you would essentially need to have a whip antenna connected to the back of both of these receivers, giving yourself 4 antennas. Using the passive splitter that you just talked about here, we can see how we can take the A antenna, the singular, passive split it to both, and do the same for the B side.
As Jason was saying, basically passive splitters in this scenario will give you the opportunity to distribute the RF signal between two receivers in a very basic scenario. Now, in case you've got a receiver that's equipped with a cascade output, basically you can use that cascade output to distribute the RF signal from one unit to the other. A cascade output is in essence either passively or actively, depending on the model type, an exact replica of the RF signal that's being presented at the entry of that unit. So if it's there, you can use that to connect to an additional unit, but please refer to your system's manual for limitations. Because as good as we try to make it an exact replica of the RF signal, there is some signal degradation in there potentially. So there are limitations to just how many cascade hops you can make. Now, if you say, okay, passive splitting isn't going to cut it for me, cascade options, I'm running out, then the next step of distribution you can go to is by using an antenna distribution amplifier. And this is basically taking this passive splitter, but then also compensating for the losses that come from splitting that signal. So in essence, you take in an RF signal and you distribute it up to 4 outputs. And then these models presented here also have a cascade output that we can use for other purposes as well. So a way you could potentially use this is come in with 2 antennas on your distribution unit, use the 4 outputs, or potentially you could even use up to 5 outputs, and basically connect that up to 5 receivers who then all share the same RF signal. So just until this point, we've spoken about distributing an incoming RF signal and bringing it to several receivers, but in lots of cases you've also got RF signals going out, like in our in-ear applications where we are actively transmitting a signal. For those purposes, we've got active antenna combiners, and they basically take an RF signal and combine it onto one single output. So they are in essence doing the same, but they just do it in the opposite direction. Another fundamental difference between an antenna distribution unit and an antenna combiner unit is the amount of power they can take, because these in-ear units typically transmit at 50 to 100 milliwatts, and an antenna distribution unit would not be able to cope with that amount of power, whilst a transmitter combiner, or an antenna combiner in this case, is designed fundamentally to take these kind of power ratings. So that's it for very basic systems. So let's see if Jason is back on the call. And Jason, you can explain us about what we do if we've got more than a single level of distribution, but we want to add more than 4 systems to our system.
Let's give this a shot. Can you hear me?
We can, very clear.
All right, fantastic. Thanks for bearing with me there, Kristof, and everyone here. I appreciate it. Yeah, okay, so medium systems. We talked about what we can do with passive combining and single level distribution. Now we're going to jump into what we call two level, where we're going to use a second distribution system here. So as you can see in this graphic, we're still using a single pair of antennas. We're still talking about a single zone system here, where we come into the single level, hit our 4 outputs, and now we're going to use the cascade output here to jump to a second DA that will feed yet another set of receivers. So earlier on, I think Kristof, you spoke a bit about how there was that one system that used 2 antennas. And I think there's some more talk about this later on, but this is a perfect example of how you can continue to cascade through multiple DAs and pass that RF system or that RF power through to multiple receivers. This is really where the DAs start to shine in terms of making sure that the levels and the signal levels are at an appropriate level to hit all these receivers that they're getting enough signal. We can take this one step further and use what I call a master DA or more than 2 distros. And this is where you're going to have a single distro feed multiple distros. And I can't tell if I'm behind on the slide or not. I seem to be having quite a few problems today. But one distribution amplifier will feed multiple distribution amplifiers, as hopefully seen in this slide, where you've got the 4 outputs on the A side and the 4 outputs on the B side are feeding the in multiple distros, which are then subsequently feeding multiple receivers. Kristof, I believe you want to expand on the case study we mentioned earlier on these more than 2 distro levels.
Yeah, well, I've just brought a bit of an example of how you can use this. We started off with this rule of thumb, right, of saying 2 receive antennas, 1 transmit antenna, and basically you've just explained this how we can start building components and adding components on to expand systems to larger situations. So I just wanted to show what that would end up looking like. So this is Friends of Amstel in the Netherlands, where we basically combine 250 channels of Axion Digital and 100 channels of PSM 1000 all together on 2 receive antennas and 1 transmit antenna. Obviously, when you start doing things like that, we explained the basic fundamentals of calculate your cable losses, calculate your splitter losses, and it's fundamental that you make sure that you target that plus minus 5 dB receive level at every receiver. But I just wanted to show this as a nice example of basically 350 channels that were all run on 3 antennas. And that's basically the only realistic, accurate way of doing this. So for the people who said, yeah, okay, Jason, you've spoken about multiple layers of antenna distribution. What do we do on in-ear transmission? Because basically, I've got an 8-way in-ear combiner imaged here. We've got 8 channels of PSM that are being transmitted on a single antenna. That all works fine, but what if I want more? And then basically we provide on the front of our antenna distribution systems, there is a passive combiner that's properly cooled and can handle the power levels of combining multiple channels of PSM all together. And what you can basically do is take the output of a single antenna combiner, take the output of another, plug them both into the A in, the B in of that passive combiner, and then it will give you a combined output signal, in this case giving you up to 16 transmitters all sharing the same antenna. I mentioned before, these units, they really excel at doing this properly. If we look at other units that are available to do this, the people who are familiar with RF fundamentals of intermodulation products and signals interfering with each other or interacting with each other, that's where we see different performances between different types of these units. And that's where I really advise picking an appropriate unit that can handle the level and the number of frequencies all being combined at the same time. So we can use a system like this easily to expand onto larger systems. So that kind of gives us an idea about our rule of thumb of 3 antennas. But there's scenarios that don't just cut it with a single set of antennas, right, Jason? There's scenarios where we say we've got more than one room. So what can you tell us about how you'd go about it, setting something like that up?
Yeah, absolutely. This is where things get really fun, in my opinion. When you need to cover more than one zone or more than one space at a time, how do you achieve the results to cover those multiple zones? So the first way is demonstrated here, where we've got a active bias T in this situation in a RF split, where we're going to take 2 A antennas in one zone and 2 B antennas in one zone, and we're going to combine those through to a DA. So essentially, you've got an A and a B in zone A and an A and a B in zone B. And those are going to now be pushed through the A. And this essentially is a simple way to achieve a 2-zone receive system. And this is using distribution and looks like ULXD, and kind of the most basic way to get a multi-zone system in this setup here. There is something I want to kind of maybe jump a little bit off topic to a certain degree for those of you in the room that use Axient Digital and are familiar with Axient Digital. Axient Digital is kind of our flagship RF line. When we talk about analog versus digital, there's one kind of very important component to be aware of, and that is that we are now accepting or taking bit stream data information at each antenna. So in this example, you see we've got an A and a B antenna, and it's transferring that information to the 4 channels of the Axient Digital receiver. Axient Digital has a special mode called Quadversity, and what Quadversity does is it borrows the receiver channels from 2 and 4 and takes those radios and allocates them to be receive radios for channels 1 and 3. And essentially, what makes this better, doing what I showed you in the first slide of this module, is the A, B, C, and D antennas that are distributed here are essentially getting independent data streams or independent sets of 1s and 0s. And we're taking all 4 of those data stream sets and then ingesting those independently. And then we can do some fun inside them to compare and contrast, for packet loss, do some error correction. And so what you see here is this floor plan where we now have four antennas that are now feeding a single Axient Digital. And you've got 4 independent true data streams that are feeding your RF, which it's kind of hard to quantify, but the reliability flies through the roof in terms of using Quadversity as a means to either expand coverage in a single zone, as seen in this drawing, or you could potentially take the C and D and drop that into a different zone as well. But it really shines when you need to cover a large stadium or arena, as seen here, and you get Quadversity set up to get those independent data streams. So that was a bit of a... Go ahead, Kristof.
I was just going to add that in essence, you've got like 4 different receivers almost listening to the exact same thing, which really adds to the reception quality on that, doesn't it?
Yeah, that's a great way to put it. Absolutely. Whereas in some other multi-room distribution setups that we're going to go through, while you do have multiple antennas, they're still coming back and feeding a single A and a single B input through a passive combination. So yes, you do have more signal from multiple rooms. In this scenario, you're dedicating basically a demodulation digital radio to each independent antenna, which gives you exponentially more data to create a perfect audio stream. So as I mentioned just a moment ago, if we were looking at more than 2 zones, this is now another example of a multi-room antenna distribution system. This is 3 rooms, A, B, and C. And you'll notice here we're using our passive splitters and some inline amplifiers, which I'm assuming here to make up for some cable loss, where we take rooms A and B's antennas and we passively combine those. And then we're going to hit a bit of an amplifier come into another splitter, which allows us to add the third room A and B antennas. And then finally, we will route that all the way back to our DA, which will then feed a stack of receivers. So this is a great way to cover a large group of breakout rooms or 3 studios or whatever your specific application may be, where you need 3 zones. Instead of having 3 receivers, 1 in each room, you can essentially take 1 set of receivers and now distribute passively through multiple rooms.
And what I'd like to add as well is that when designing this, really look out that you put an A and a B antenna in each room to protect that diversity reception across the floor plan. That's is really going to add to the reception quality in this system.
I think you mentioned earlier, Kristof, that we weren't going to talk about multipath and wide diversity, assuming most of you are aware of that situation. But yeah, that's the point. You know, continuing, and I go as far as, like, if this drawing is accurate in terms of how the building is actually set up, I make sure that it is indeed an A and then a B and then an A and then a B from right, so that you're really creating some diversity between the room B and the room A's A and B antennas, right? So that you're stepping those B then A then B if it is linear. And I think a couple slides from now, there's an interesting graphic about how to set that up as well. But kind of some next level stuff here. This one's interesting to read. A lot of the slides previously were laid out left to right. This one I like to start on the right side of the slide. That's just how my brain works. But the antennas are on the right side. Those are more of an install system, the UA846 US. But if you read this slide right to left, you'll see that the first 3 antennas are going to be the A side of 3 separate rooms. The second 3 antennas would be the B side of 3 separate rooms. And this is just another way to achieve the splitting and the powering of those, the bias to those units, to get that passively to usable antenna distribution locations. I never noticed the cable spec on this diagram until right now. But yeah, Kristof, that's some of that stuff that's passive. Would you like to talk to us about some active combining?
Sure. We've got this slide still on the screen, I think, of a large area antenna coverage. I think, well, it's kind of to the slide you spoke about, right? Isn't it, about how you would lay that out on a map in a broader area? So that's just to say they don't necessarily have to be in a room. They can be, if you want to get coverage over a large scale area, this is what a floor plan could look like, and trying to protect the diversity in as much positions as possible. But yeah, as you say, as you just brought up, Jason, if you want to combine those antennas actively, because what we saw is every time in your schematics there was a passive combiner, we have to take that 3.5 dB loss into account, which we then have to compensate for, and the calculations get, well, tricky, fairly easy. So we could use one of our active antenna combiners, or our in-ear combiners, as we'd like to call them sometimes, to do exactly the same purpose, but in a neater, active way. So these units, as they can be used better to combine multiple transmitters, we can quite easily do a small service modification. So they provide DC bias to antennas, and basically feed a set of antennas and combine them all into a single output. So if we look at the schematic of what that would look like, is on the left here, we've got a 4-way antenna combiner that basically gets the signal off of 4 antennas, combines it into one output, and then feeds that signal into a distribution unit. And on the right, we do for the B side exactly the same thing. So basically this active unit would replace the whole diagram of bias Ts and passive splitters and everything that we had in there into a single unit. So if we take this way of actively combining multiple zones and then distributing it out, it kind of brings us to a case study of Fête de Vigneron in Switzerland, where basically this system was used to combine 324 channels of Axion Digital over multiple zones, because the reception area was so significantly large that we couldn't just cover it with 2 sets of antennas. So this is the first time that I step away from my rule of thumb of 3 antennas per system. This is basically, we said the reception area is too large. We're not going to get away with a single set of receive antennas. We need multiple receive antennas. And basically active combiner units were used to take 4 sets of antennas, 4 diversity pairs, combine them into a distribution chain behind that to 324 channels. So with that, I think we covered a bit small, medium to large, and we've reached the end of what we had to say. And then we're very keen to learn what questions you may have from this.
All right, great information, everybody. Thank you. Turn my camera back on here. Okay, just pulling up my Q&A here. First, we've kind of grouped these into some subjects here. So we're going to start with questions about notch filters. Does Shure recommend using RF notch filters with their antenna systems in difficult environments?
I can take this if you want, Jason.
Yeah.
I would definitely say that if you know what you're doing, if you know what the problems are you're trying to solve, notch filters are a very, very good way of cleaning up the RF spectrum. One of the things we didn't really dive in today is just how much noise an RF reception unit can take before it starts saturating with out-of-band noise that you really don't care about. So using a notch filter to say, hey, look, my receiver is in this part of the spectrum and I'm going to ignore all the rest around that, will definitely clean up your signal. The caution I would say there is be very careful, because it wouldn't be the first time where I see somebody using a notch filter, then changing the frequency throughout the show or throughout the tour and tuning out of that notch filter range. And that obviously is going to give you some issues. So yeah, if you know what you're doing, if you've got a notch filter perfectly within the reception band of your receiver, they can definitely help you clean up the signal.
Okay. And does Shure manufacture notch filters?
I'm turning to Jason on this. I think at this point we do not.
No in notch filters. Nope. There's front end filters on the DAs and the receivers, but no inline notch filters.
The closest we get, I think, is on our Axion distribution unit. There is like a set of filters on there that you can select between. So I've seen many situations where they use that to at least, I wouldn't call it as narrow as an actual notch filter where you really pick like 10 or 20 megahertz out of the spectrum, but they are fairly tight. So yeah, the AXT 630, if I'm not mistaken, will be able to filter a significant part of the spectrum already.
Okay. Next, we had some questions about the possibility of using different manufacturers' receivers and antennas. Is that possible? Can you mix and match antennas and receivers from different manufacturers?
Yeah. Yeah, we mentioned earlier, all you really need to care about in terms of talking about distributions components, DAs, combiners, antennas, and cabling is to ensure that it's rated for the frequency band that you're operating in. Pretty much across the board.
Yeah. The small side note I put there is, again, we brought up the power rating because it is quite easy to find, let's say, third-party distribution units that look like they're going to do the trick, but then once you start loading 16 channels of transmit onto them, you start running into issues. So if you check the specifications, if they're in band, as Jason said, if they can handle the power, you should be good to go.
All right. We have a lot of questions about cable loss and cable loss calculations. So first of all, can you talk a little bit about how to calculate cable loss?
So there's the way that Kristof mentioned in the slide, where you're taking the manufacturer's numbers and putting those in basically a line graph and saying, what's my overall guesstimated loss or gain based on the numbers that are listed. So the cable manufacturer, whichever cable you purchase, will have publicly stated what the loss of their cable based on a certain amount of feet or yards. And that is generally true for a period of time post purchasing that cable, assuming that it's well taken care of. The more advanced way to do this is to get a spectrum analyzer that has a tracking generator. And a tracking generator will then generate an RF signal at a certain level, neg 60 dBm, and you'll take the output of that level through your entire system or through the cable that you're looking to test, plug back into the spectrum analyzer, and that analyzer will read the difference between that output of neg 60. So if it's now coming in at neg 57 or neg 63, you'll be able to measure the gain or the loss based on the cable that you're using, and then you can do that through the entire chain, all pre-antenna essentially, and that's the more advanced way to get some specific measurements on your loss and gain.
All right, great. If you want to kind of avoid worrying about the calculations, is there sort of a recommended maximum cable run?
Really depends on the cable type. As Jason said, every cable manufacturer will have a spec sheet against it. The thing I want to add to that point as well is cable losses are frequency dependent. So really look that you pick the right number of the sheet. Because a cable loss at 300 megahertz is going to be different than at 700. So make sure you look at what frequency your system is using, read the correct value, calculate that. And as Jason said, if it's a new cable out of the box, I would take that spec sheet for reality, because that's going to be plus minus 10% of what the reality is.
And can you speak to anything about 50 ohm cable limits?
I'm wondering what limits we mean by 50 ohm cable limits. I'm guessing it's the same question as about what the maximum length is. To be fair, you've got cable losses. The cheapest cables go as low as 40 dB loss over 100 meters. The best cables out there go as low as 0.8 dBs over 100 meters. So really, how much do you want to spend on your cable is my answer to that. It's very hard to define a maximum cable run, because if you're willing to spend a couple of $1,000s on your cable, you can get away with a lot more.
Yep.
Gotcha. All right. Another question about cables. I was once told by a Shure engineer that if I remote a unit's antenna, I may have to use a larger antenna than what was supplied with the unit. When is this and why?
I'm confused as to where this came from, because I really see antenna type based on the, let's say, the air travel distance. You've got the distance between your transmitter and your receive antenna, and that's what defines what your antenna type is. And then you've got the cable distance, and that defines whether you need an amplifier on your cable or not. And the two are really not directly related, unless, Jason, you want to add something else to that?
No, I think you nailed it. I'm curious if this is in terms of like the width that comes with the product, the standard dipole, and then depending on, like as you mentioned, how far is the distance from antenna to transmitter? Are we talking about a directional antenna, like an LPDA helical, to achieve the distance between antenna placement and the actual transmitter? So yeah, again, you're gonna dive into types and antenna placements and the passive forward gain that is based on the physics of certain antenna designs.
Well,
I think there's also an issue of quarter wave versus half waves. Sometimes systems are provided with quarter waves.
Yeah. Well, and there's the additional, I could easily see me almost giving that answer. I'll elaborate a bit more on the answer, but if your antenna for some reason is a distance away, I could see myself saying, yeah, go for one of the active LDPAs, because that's got an amplifier built in, and then you can get away with a cable run. So that would be justifying why we say use a different antenna. But again, it depends on the case. Really hard to know without knowing the background of the project. Giving a correct answer is difficult.
It looks like this is in regard to with some of the Whether it's Shure or another manufacturer, that quarter wave antenna specific to the ground plane, that if you have to extend that antenna out, that you cannot just simply take the larger rubber ducky half wave out of the box and simply go put it on a mount 25 feet away, that smaller quarter wave, you basically have to create a whole ground plane system. Exactly. So those you really do not want to try to extend. It's much more effective and efficient to buy the larger half wave antenna. Now it makes sense.
Awesome. So we kind of talked about this a little bit, but there was a series of questions about how to determine which antenna to use when, half wave versus LPDA, just sort of all of those questions. So are there any sort of wrap ups to that previous conversation you want to talk about when to make an antenna decision?
Dangerous rabbit hole to dive into, really, antenna types. And I mean, we do our wireless mastered seminar, which typically takes best of a day, where we really dive into how do you make those kind of decisions and antenna placement. It's really the fundamentals is look at your room. What positions from the antenna are you going to be transmitting from? Are you going to go behind the antenna? Then you definitely need an omnidirectional to be able to receive 360 degrees around that antenna. Is all the action going to take place in a single point? And LDPA antennas are probably a better choice because they're a bit more directional and they block all the RF from the back. But really, it's a case-by-case scenario and very difficult to answer in a 30-second question.
All right, sounds good. Understandable. Next question, regarding antenna distribution, how many levels can you go down?
Jason, do you want to take this one?
Yeah, I mean, I think in the case studies that you covered there, Kristof, is a pretty prime example of how many levels we can get moved through DAs, assuming that you follow the rules and the parameters of proper distribution in using DAs to get to each level. You're going to have the proper loss compensation with an active distribution system that allows you to continue jumping for an pretty much exponential amount of time. As long as you're calculating your loss and using a proper amplifier, I don't see a situation where you're running to an end point.
So really, it's typically when we get to the case studies we've done, we did the approach that Jason said, the professional approach. So basically, every path to every receiver was measured to confirm that we're still within acceptable values. And as long as you do that, you can get away with quite a lot. The only thing I would say is, because I often get the question like, hey, you talk about antenna distribution, and like we did on this webinar, explaining why we need it. But I've got 4 receivers stacked on top of each other and they work just fine. And to that point, yes, in that particular scenario, it may work just fine, but you may be just on the edge of what you can get away with. It's very similar in stacking multiple distribution units. You may stack 20, cascading 20, and it may still work because you're within the threshold of what works in your scenario. But you will have significant losses. So basically, when you start building constructions like that, do your measurements and make sure you compensate for gain losses across the chain.
Yeah, I think it's important to note one thing that is kind of a misconception is that a DA will across the board if something were to go wrong at a component level in a DA, and that's not true. You can have a single port on a DA that has a failing component inside of it. So if you feel as if you've got one receiver that just consistently has low signal for some reason, it is definitely worthwhile to maybe just swap the cable to a different port and see if that comes back up to help troubleshoot that. And that goes into saying, if you're gonna go multiple levels to distribute, you now have multiple points of failure. And as Kristof mentioned, making sure that you have a way to test all of those ports and ensure that they're performing as expected.
I think to just wrap up this question, the rule of thumb here to say, if you don't want to bother with calculating, measuring, blah, 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 if you stack up to 2, and that's also what we say on most Cascade boards, if you stack up to 2 units, you'll get away without calculations. Once you start going deeper, try to get some hearing equipment out and make sure you're still in a safe spot.
Great. So speaking of combining, how do you combine more than 16 IEM units?
Well, very similar to the example we had of basically passively combining those two. There are ways of using active combiners in there. I have to admit, sometimes we divert to third-party equipment to do that, all depending on the amount of power you want to handle. The biggest issue of going to higher channel count is that you start summarizing all the output powers of all the in-ear transmitters. So in the end, you end up at a watt, 2 watts, 3 watts of power that needs to go through that system because you're combining all of those transmitters at the same time. But our active combiners get away with 250 milliwatts of input power at the entry. So you could theoretically feed four ways into an input and then start stacking up like that. Or the alternative is using passive combiners to combine multiple layers at that level as well.
All right. There are a couple of questions that I saw coming in regarding our wireless master classes and seminars. And if you're looking for more information for those, I would advise visiting the Shure Audio Institute page on our website. You can easily get there by going to shure.com/SAI. Shure.com/SAI, which stands for Shure Audio Institute. There's lots more information there about trainings, master classes, certifications. So go there and explore for all of your additional needs for training. Michael, have you seen any other questions or topics come up in the Q&A that we need to touch?
I was going to say, I think one more. It looks like we got time for one more question, and I know this is a little bit of a misconception, and always comes up, especially in the systems integration world. The difference in 75 ohm cable, which is typically specified for video, versus 50 ohm antenna cable. What is the pros and cons if somebody accidentally pulls one in? Can you use it? What's the issue? And again, what's best practice?
Definitely best practice is to use 50 ohm cable. All our antenna systems are 50 ohm. So we can be very fundamental saying use 50 ohm cables and use 50 ohm equipment. All that, if you use accidentally a 75 ohm cable, if you accidentally mismatch those, all that's going to do basically is generate a higher loss. So if it is a short 2 feet or 30 centimeter type cable, you're probably going to get away with it. If you do a very long 100 meter cable run with 75 ohm, you're going to get into trouble. So basically try to separate those, really try to separate 50 ohm cable from 75 ohm cable, try not to mix and match, and that's definitely going to give you the best performance.
Fantastic. Well, I think that gets us up to time. Thank you so much, gentlemen, for all your great information today. For those of you attending, if we didn't get to your question, or if you have another question, or if you need some help with a specific antenna distribution, you can always open up a ticket with our support team. We've got a great team of guys and gals that can answer so many audio questions, including antenna combination and distribution. And you can reach them very easily by going to shure.com/contact and fill out the form there to open up a ticket with our support team. Thank you so much for joining us today. We hope you learned a little something. I know I always do, and we hope to see you on the next one. Have a great day, everybody.